Hello and welcome. I'm Dominik Freidenberger and this is a joint work with Liat Peterfreund. This paper introduces a new way of using logic on words. Our initial main motivation was information extraction, more specifically mapping a word text into a database table. You can see that as querying a word like one would query a database. But the whole framework can be used more generally, so if you care about logic on words, if you care about properties of words, this might be relevant to your interest as well. This all was prompted by something called document spanners, a recent hot topic in database theory. But as you shall see, it's more general than that. When I talk about logic in databases, just a short introduction if you didn't know that before, or refresher if you did. Relational algebra, as it's used for relational database today, is essentially just a different form of using relational first-order logic. And more specifically, a lot of the results in database theory can be summarized very, very briefly as restricting the structure of a formula makes the formula more tractable. So if we focus on a fragment like the extension positive fragment, bound the width of the formula, more about that later, or look at cyclic conjunctive queries, which can only share variables in a very, very bounded degree. That's a formal description. Then everything becomes tractable, and then we go from NP completeness, for example, to actually polynomial time and low polynomials. And that's something that we want for our logic as well. Before we go there, let's briefly talk about those spanner things. Spanners were introduced in 2013 as a formal way of describing IBM System T, a system for information extraction, and are now even used for that. Aside from all theory things, the practitioners use those formula for query optimization. The main idea is basically we take a regular expression and then build a relational algebra around that. So the atoms of our query languages are regular expressions variables. You might know those from text editors. Most of them have them nowadays. And when you match, then every variable leads to a column in your table. And in those columns, you keep intervals of positions, the location where the match was. That could also be an automaton. And on top of that, you put a relational algebra using union, in logic terms, disjunction, projections, so existential quantifiers, join, conjunctions, differences, negation, and sometimes string equality, where we look at two different intervals of positions and compare whether they describe the same word in the text, hence string equality. The first three, union, projection, join, if you use those, you can start with an automaton or convert your expression into automaton, then apply those, and you still get an automaton, although if you use join, you do a product construction and the automaton might grow exponentially large, but it all works in that. And a lot of that work of the work on document spanners has been limited on those regular spanners because they play nice, you can map them into an automaton. Things change when you start using string equality, that one here, which you might use for things like give me all email addresses that occur twice in the text and so on, just to compare things and check whether they're the same. So string equality is an essential part of IBM System T. That's why it's part of the core functionality. That's why the original paper called them core spanners. Now, so far, so good. Spanners look like relational algebra. There's just one small problem. They don't always behave like relational algebra. In particular, if you take a spanner, a core spanner, the ones with string equality, and you want to check whether the result is non-empty, which leads to all things like evaluation and model checking, that's NP-complete. So far, so good. That's something that's similar to relational algebra in the database setting. That's not a problem. But if you further restrict this and say and only look at queries that are acyclic, so information is shared in a very specific way, which in the relational setting turns things tractable, it doesn't work here. Things stay intractable. So one of the main tools of database theory does not apply to spanners. And our question was, can we have a model that gives us the same way of querying text in a relational algebra or first-order logic way, but has the nice algorithmic properties that we get in the database setting in our string querying setting? So our natural reaction was, let's look at logic. And if you look at logic on words, then there's an elephant in the room. You might have heard of it, MSO. Monadic second-order logic, or the less powerful first-order logic, on ordered structures. So in this setting, we take the universe, a set of positions, or word is a sequence of ordered positions, and then predicates for every possible letter in our terminal alphabet saying this position is an A, a B, or not. And if we then take first-order logic and allow variables for sets that can range over sets on this universe, monadic second order variables, we get exactly the regular languages. So far, so good. There are small problems with that. First of all, you can't express concatenation. You can't take arbitrary factors of your input word and then say, I have y and z, and y concatenated z is equal to x for a third factor. You can do that for a bounded length, but not arbitrary lengths, because that's not regular. You can't say those two factors contain the same word, because, well, string quality, that's not regular. Second order variables are also very expensive if you want to study the complexity of evaluating a formula from the structural point of view. So that's not nice. And also MSO is not very user-friendly. So relational algebra, one of its strengths is that practitioners can use it to optimize their queries. If you convert your query into something using second-order variables, you don't have relational algebra, or people have to understand them, that gets very complicated very quickly. There's another big logic on words, theory of concatenation. There we basically have one fixed structure, just take all possible worlds over a fixed alphabet as our universe. Then as a function we can take concatenation, can stitch them together, and then we get constants for the empty word and for every letter that we might want to use. And theory of concatenation, you can see that as first order logic using this structure. Or alternatively, you start with the basic building blocks. As atoms you have word equations that consist of so-called patterns with variables and terminals, and then you replace those variables, multiple occurrences the same way, with terminal words, and this thing is satisfied if both sides have the same word, if both sides become equal. And then you can add quantifiers and conjunctives like usual. So this, the upper one says, well, wxx, the word is a square, and then the formula is true on inputting a word w if w is not a square because of the negation here. Likewise, this one here, xy, is satisfied if x and y satisfy that equation. xaby is ybax. There's only one problem with this way of doing logic on words. Satisfiability is undecidable, and we can't just say what about model checking instead, because that's undecidable as well, because there's no meaningful distinction between model checking and satisfiability. So what we do instead is we forget about MSO. Instead, we look at FO like it's used on databases, FO over finite models, where our universe is some finite set, and we have relations functions constant. That's a standard FO finite model setting. Their satisfiability is still undecidable, but model checking is a different problem. If we fix our structure, just want to know whether an assignment is true, is p-space complete and becomes NP complete for the existential positive fragment. So that's a setting where databases are normally based. On the other side, we take the theory of concatenation, like I mentioned before. Satisfiability is undecidable, and their model checking, there's no meaningful way of defining model checking that avoids the undecidability problems. So with that. And now we combine both. To get the logic of the finite model version of the theory of concatenation, we take as a universe a word and all its factors, which is a finite set, and we just keep concatenation as our function, and then the empty word and every letter as constants. So we still have word equations. That's the main idea. We take the best of two worlds, and as we shall see, that solves many of the problems we had with the theory of concatenation. The logic uses as atoms word equations of the form x equals alpha, where x is a variable, a single variable, and alpha is a so-called pattern consisting of variables or terminals. We don't need this restriction that the left side only needs to have one variable, but the formulas are easier to read if we have that. There's more about that on the paper. Just ask me a question about that. We fix one special variable called u, the universe variable, that shall represent our word we're talking about. So you can see it as the input word, the word everything's working on. Technically, it's a variable because we didn't want to change semantics compared to word equations too much, but we shall use it more like a constant because that will contain the word we're talking about. And as connectives, well, we use conjunction, disjunction, negation, and quantifiers. We will not quantify the universe variable because the universe is fixed, and we will not treat it as a free variable. For all purpose, we need one because it's fixed, it only has one value. And that's all we need for syntax. So atoms, the word equations, and then stitch them together with first order logic. Now for the semantics, our interpretations we take a word representing our main structure and, well, the universe by taking all its factors later on, and a partial morphism that takes variables and constants terminals as input and maps them to terminal words. In particular, we shall say that, well, U, the universe variable, always contains the word. That's fixed. Constants are constant, so all the terminal letters that we have will not be changed by the partial morphism. And then if we have a variable, it can only be mapped to a factor of our main word, of the input word. Long story short, from a first classical logic point of view, it's just our universe as a set of all the factors of the word, and then we can only match something in there. And constants are constant. And that's it. And then to define the semantics, this interpretation satisfies the word equation. If the variable on the left side replaced and everything on the right side replaced gives us the same word from sigma star. That's it. And everything else just proceeds accordingly. Conjunction, disjunction, negation as usual. For the quantifiers, well, we pick one word from our universe that has to fit into W, and that's it. That gives us everything. If we have a sentence or a formula without free variables, we just ignore the sigma because we don't need it and just write W satisfies phi. That's that. Everything fits on one slide. So before we go to the results, two quick examples. Of course, they're more on the paper. If you want to express a simple query, just a Boolean query, asking, does my word W contain, for example, papaya or banana? You write, is there some factor x such that x is papaya or x is banana? This is also something you could express in MSO or FO on a linear order, of course, but to write it down explicitly, you would have to say
there are positions x1, x2, x3, x4, x5, x6, and the first one is a and p, and the second one a and p and a and y and a, or the same for banana, and they are all successive.
It's a whole lot of writing. Here you can just write it down like this. This one is more interesting from that point of view. It says, give me all factors, so return, because we have a free variable here, that occur exactly once in W. This one, this, we can decompose our main word into factors p, x, and s, just cutting it into 3 pieces. And we cannot find another decomposition that does the same thing, but the start is different. And that is something that you cannot express in MSO, because you need to do something like string equality. You could only do it for factors of a bounded length. That's the main advantage. We can reason about words as words, not as sequences of positions. So we can concatenate them. We can look at factors, compare them, no matter where they occur in the word, straightforwardly, just by using the word equations. So we can express some things quite conveniently and easily. Of course, coming from the theory of concatenation, which is undecidable, the question is, can we decide that one? And if yes, how expensive is it? So let's look at the model checking problem. Given a theorem, a formula of free variables, and a word, does the word satisfy the formula? That's the question. This also can be used for things like evaluation, where you have free variables and enumeration of the results and so on. But let's focus on the basic problem first here. And the results we have as well, data per complexity, the one where we fix the formula, is in log space. And in general, if the formula and the word are part of the input, the problem is p-space complete, and it becomes NP complete if we look at the existential positive fragment. That's exactly the same that we have for first order logic over finite models, so that's already nice, and the proofs are the same. We can just guess the contents of the variables. Lower bounds are also just reworking the proofs from there, and it gives us a nice side result. The lower bounds still hold if we just look at a word that consists of a single letter. So we have the same ballpark tractability range. We are not in polynomial time, but we are quite close. And the question is, can we further lower things using the same way as in FO? There we look at the width of formula, the maximum number of free variables in any subformula. In FO, fixing that gives us tractable model checking, and same as here. If we have a formula that has a bounded width, then this goes into exponent of the complexity. So if k is fixed, everything becomes polynomial time. Not good polynomial time, but we're working toward that. Main idea is the same as for first order logic. You just materialize each word equation into a relation. If your width is bounded, those lengths of those size of those will be bounded. Then you evaluate, and that's that. So fairly straightforward, nothing problematic here. We also went beyond that. We can split FC atoms the word equations, the right side of the word equations, into small formulas, into conjunctions of equations with only two variables on the right side. And that can be done in a way that bounds the width depending on the tree width of a pattern. We first have to define the notion of tree width of a pattern. Various other criteria that are used in finite model theory apply as well. So as soon as we've materialized our word equations, we can talk about bounded tree width of formulas and so on. All those carry through. Often we can do better by just splitting apart the word equations into smaller formulas, which is a big area for, we only started that. There's a lot to be done about how to best split formulas and reduce criteria like width. Now we are in the same region of expensiveness of model checking as first order logic on finite models usually is, and we can use the same criteria to lower the complexity. In this case, we get to something like polynomials of a bounded degree. And if we look more carefully in the structure of the query and perhaps take in other factors, we can also get to low exponents in our polynomials, and perhaps even in some cases below quadratic time. But that's for future work. So we get tractable model checking, or at least as tractable as in relational databases. The question is, do we have to pay a price for that? In fact, yes, we do. Let's look at static analysis and satisfiability. The first thing we have is that even if we look at existential positive formulas that only use 4 variables, so with 4, we can't decide containment if you look at them as language generators, because if we don't have any free variables, our formulas say yes or no to words, so we define a language, and then we can check the inclusion problem for that. That's containment. That's undecidable. Given 2 formulas, if we want to know if this describes the same language, undecidable. Given 1 formula, I want to know, is it a pattern language? So that's one that's just defined by taking one of our FC word equations and then existential quantifiers to quantify everything away. That's a pattern language. That's undecidable. If we want to know if the language is regular or expressible without using any variables, so FC0 is not as trivial as it might seem. It's the finite and cofinite languages, class of those, or the universal language sigma star. All that is undecidable, and essentially, you might have guessed it, that's just one proof for all the others follow as consequences, because what's undecidable is this part. So that's undecidable. And the consequence of that is we have non-recursive trade-offs. Let's first talk about recursive trade-offs. You know, for example, going from NFAs to DFAs, the trade-off is exponential. The blow-up is exponential. There are settings where you have double exponential blow-ups and so on. In this case, the blow-up is not bounded by any computable function, which is a bad news because it means we can't reach it. But on the other hand, if the trade-off to singleton sets means that we could write straight-line programs in FC4 that can reach arbitrary degrees of compression. So for every degree of compression we pick, we can find a word where the FC formula is that much shorter than the word we have behind that. Also, regarding satisfiability, it's still undecidable. We only need 3 variables to prove that. FC0, that's just finite and cofinite sets. So in that case, it's trivial, and it's open for 2 and 1 variables. Other open problems that we run into, well, the big one that we would like to answer is, can we minimize width computably? Given a formula from some nice fragment, existential positive, for example, compute the one that uses the lowest amount of width. That would be very, very advantageous. That's open even for small fragments like conjunctive queries and so on. And likewise, we don't know whether adding more variables gives us more expressive power. We thought it's obvious. We still think it's the case, but the proof that we had in mind failed because then things could be expressed. So inexpressibility in that fragment is a big open problem. In fact, inexpressibility in any fragment is a big open problem. But before we talk about that, before we talk about inexpressibility, let's talk about spanners that I mentioned initially as a motivation. FC, as we defined it, cannot express everything that a spanner can do. So, for example, if we look at the existential positive fragment, it can't do 2 star of a proper subset of our variables. And that's because that's not even possible in the existential positive theory of concatenation. We inherit this inexpressibility problem as it results from combinatorics in words. We have a key solution to that. We extend FC with regular constraints. So we can take a regular expression like rho here, and then just write x as an element of rho. That expresses this factor x belongs to the language of the regular expression. That's that. And we can get away with this as far as model checking is concerned, because this doesn't spoil our complexity result. Everything that was tractable is still about that tractable. Perhaps our polynomials, depending on how we do it, might change a little bit. You can also do that with any other constraints that play nice in the way you're exactly treating your formula. So if you do the brute force evaluation that I mentioned on the previous slides on model checking, if you have something where you can build the table somewhat efficiently, or if you have something where the constraint can be answered efficiently, then you can hook it up into your algorithm and extend your logic to the purpose you have in mind. It just gives you a nice way where you can still look at the structure of the query in FC and then tie in the constraints and then think worked. And based on that, we can connect to spanners. If we take FC with regular constraints, that has exactly the same expressive power as generalized core spanners, and the existential positive fragment is the same as core spanners, and the conversions are in polynomial time in both directions. We can do that. In fact, for convenience, we also looked at a different way of defining first-order logic. So you do first-order logic like with MSO on an ordered structure, but you add regular constraints. Now they're binary because we have start and end of the factor we're talking about, and string equality, which is for array because 2 for 2 strings, 2 each for 2 strings, and then can do that. The only difference is FC can simulate those things exactly by expressing positions as prefixes. Spanners and FO on ordered structures can only simulate modular string equality because they have to express everything as an exact position in the word. And if you want to say, if you want to just represent a factor, you need to decide how to represent it. So it's more like a one-to-many reduction. And now for more general inexpressibility, because that one was taken from the theory of concatenation, we have one more inexpressibility way result that's not specific to that and even works with negations. So the language AN, BN cannot express in FC without regular constraints. And we can prove that by just going into finite model theory using the finite Feynman-Wald theorem. But we can also extend this to F3 with regular constraints. It's using a technique from combinatorics on words where we can express bounded languages using formulas that do not use any constraints. We can remove the constraints of the hypothetical formula that we have. So if we could express it in FC-reg, we could express it in FC. So for this result, we need to combine a lot of finite model theory in a way of using the theorem and quite a bit of combinatorics on words to get the result that we want. And as FC-reg has the same expressive power as generalized core spanners, this gives us the first inexpressibility result for generalized core spanners that's not relying on things like decidability as an argument or only works on unary alphabets. That's the first somewhat general thing. But it only works because we're pairing techniques from two different fields together, and the structures are very, very restricted, just being A and BN, which is not that interesting. There's a lot of work to be done in the future. Another thing that we looked at, another way where FC behaves very similar to FO, is descriptive complexity. So if we extend our logic with deterministic transitive closures, least fixed points, or partial fixed points, if you know your finite model theory, using those and FO with ordered structures characterizes various complexity classes, then our result here is the same. Even if, and that's different from FO and other structures, we only look at the existential positive fragments. That's very nice. And if you care about data log, then all this can also be used for data log on words. If you don't care about data log, disregard that part. Wrapping things up, what do we have? We have a new logic on word that behaves like FO in relational algebra, at least regarding things like model checking and descriptive complexity. The price we pay for that is static analysis and optimization become complicated, undecidable, or at least complicated in general. We don't have a proof for the optimization, it's a bit lowering. But we also show some way, even though I skipped it in the presentation here, of lowering the cost of that. And if you care about the more practical sides, we can directly map FC into relational algebra on text that could be used by practitioners for things like query plans. So we have a logic that can be used as a logic for spanners, as a representation of spanners, where we can then work in a more logical way. But we can also use it more generally as a framework for converting textual data into relational data or deciding properties of words. Many open problems remain, and that's it. Thank you for your attention.